Okay, we're looking at lattice paths. Well, what is a lattice path? An integer lattice is a set of all points in the Cartesian plane for which both the x and y coordinates are integers. Now, if you're used to drawing graphs on grid paper, this will be an integer lattice path, where these grids, where they intersect, are the points that we're going to follow. So we call that an integer lattice path. If you like to draw graphs, that is what you'll find. A lattice path is one of the shortest paths connecting 2 points on the lattice. So moving only horizontally and vertically. So for example, if we want to go from 0, 0 to 3, 2, we can go 1, 2 to the right, 2 up, and another 1 to the right. Or we go 2 up, 3 right. Or we can go 1 right, 1 up, 2 right, 1 up. Or 1 right, 1 up, 1 right, 1 up, 1 right. Again, so there's quite a few ways in which we can reach from point O to point 3, 2. Okay, so notice now, to ensure that the path is shortest, each move must either be right or it must be up. Okay, you can't go right, right, up, left, down, right, left, and repeat directions. So you can only move, that's what it's saying, to make sure it's shortest. You can only move up units, or you can move to the right with the unit. So let us see exactly what it is that we are looking at when we look at the lattice paths. Okay, so let me just get that ready for us. There we go. So the last bit here asks, additionally in this case, note that no matter what path you take, you must take 3 steps to the right and 2 steps up. And we saw that quite quickly. That's how we need to move. Okay? So, no matter in what order you take these steps, there will always be 5 steps. Thus, each path has a length of 5. So if we talk about it as a bit string, the bit string will have a length of 5. Okay? 5 in total. Then, now for the counting question, how many lattice paths are there between 0, 0 and 3, 2? We could try to draw all of these, okay, but instead, drawing all of them, maybe just list which direction we travel on for the 5 paths. So remember, we had 1, 2 going up, 3 going to the right. Okay, so we said we can go 1 there. We want to get from here to here. So we can move right, up, right, which is 5. That will be RU, RU, R will be our code. RU, RU, R. Okay, or we can go up, so up, and then R, R, R. Or we can go R, R, up, R, 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 up, R. I think it's starting to become clear here that there's 5 steps here. And if we now choose to represent our movements using a bit string, our bit string will have a length of 5. We're always going to move 3 units to the right, no matter what we do. So if we say that the U's are 0s and the R's are 1s, if we move to the right, we have to move for a length of 5 and a weight of 3, no matter how we move. Okay, now we've already seen some interesting things about that type of path. So notice that each of these strings have 5 symbols, exactly 3 of them are R. Since our destination is 3 units to the right, this seems very, very familiar with what we've done. Okay, so if we represent them with noughts and with ones, we could have done it the other way around, doesn't matter. We just decided to do the R's as our ones. Then we should just have 5 strings of weight 3 in this case. So there are 10 of those. So what does it mean? There's 10 paths to go from, shortest paths by the way, to go from naught here to 0, 0, which was located there, to the 0.32 on the lattice. That is where my finger is at the moment. Okay, so the correspondence between bit strings and lattice paths does not stop here, folks. Here's another way for us to count the lattice paths. Consider the following lattice shown below. To get to that point there, every single path will either pass through point A or through point B. There is no ways they can skip either of those points. So it's either going to go through there or here. It's not going to go through both at the same time, because that would mean we went right, down and up again. Okay, so it goes through one of those two. So we say that any lattice path now that starts at 0, 0, 2, 3, 2 must pass through those. Now point A is 1, 2, 3, 4 steps away. Point A, here, I'm going to do it on my form here. Point A is 4 steps away. Point B is 4 steps away as well. So both of them are 4 steps away from the original point 0, 0. Okay, so the number of lattice paths of A is the same as the number of 4-bit strings of weight 2. 4-bit strings of weight 2, so meaning 1, 2, 3, 4, of which 2 moves to the right, or 4-bit strings with weight 3 R's. So to get to that point, because we need to move between those two, we have a length of 4-bit strings with a weight of 2, or 4-bit string with a weight of 2, or we can have a 4-bit string with a weight of 3. And we see that exactly what happened before. If we look at the cardinalities of these sets, we again have 6 of those, we have 4 of these, and together there's 10 ways to do that. Okay, so the point B is 4 steps away, we said, 3 of them to the right. Okay, and the other one is 4 away, 2 of them to the right. So the total number of paths is 6 plus 4. This is the same way in which we calculated the 5-bit string weight 3. So the point and the takeaway here is the exact same recurrence relationship exists for bit strings as what exists for lattice paths. Okay, now next video we will focus on binomial coefficients.